Alrighty, we are going to be talking about the chain rule in this video. So here, I'm going to do probably the first two functions. Let's say that I have x plus 1 square and 2x plus 1 square. If I were to expand out x plus 1 square, I'm going to get x squared plus 2x plus 1. And if I take the derivative of that, so that's just going to be 2x plus 2. Which, if I were to factor that, that's just going to be 2x plus 1. Now, I kind of gave you the power rule based off of this right here. And notice how here, these match, so there's not really a missing factor. So that's just going to be 1. Now, for number 2, let's say that I were to expand that, and that's going to be 4x squared plus 4x plus 1. And if I take the derivative, that's going to be 8x plus 4. And if I were to factor that, I'm going to get 2x plus 1. And notice how here, if I do the power rule based off of this, I get 2 times 2x plus 1, and that doesn't match up with my factored derivative. So here, what I need to do is multiply this by 2. Well, I could do the same thing for, let's say, this one right here, where I have x squared plus 1 square. And if I take the standard form of that, that's going to be x to the 4th plus 2x squared plus 1, or 4x to the 3rd plus 4x whenever I take my derivative. That's going to give me a factored derivative of 4x, and then x squared plus 1. But if I were to look at my power rule based off of this, that's just going to give me 2 times x squared plus 1, and I'm missing 2x. Now, if I were to do the same thing for, let's say, the last one, where I have 24x squared plus 24x plus 6, and I take a GCF of 6, that's going to give me 4x squared plus 4x plus 1, which is also the same thing as 2x plus 1 squared. So this right here is the same thing as 6, 2x plus 1 squared. But I'm missing 2, because this is 6 and this is 3. Now, based off of this, I have a missing factor of 1, I have a missing factor of 2, I have a missing factor of 2x, I have a missing factor of 2. And now, I want you guys to think, where do you think we're getting these missing factors from? And I give you a little hint. What relationship do you see in relation to the inside function of my functions that I give you? So let's say x plus 1, 2x plus 1, x squared plus 1, 2x squared plus 1, and 2x plus 1 in terms of, let's say, the derivative. And if you were to look at that, the derivative of my inside function is 1. My missing factor is 1. The derivative of this inside function is 2. My missing factor is 2. The derivative of x squared plus 1 is 2x. The derivative of 2x plus 1 is 2, which means here, if I were to take this derivative, my missing derivative should be 4x. And if I were to do this, I'm going to get 4x to the 4th plus 4x squared plus 1, 16x to the 3rd plus 8x, 8x, let's see, 2x squared plus 1, and see how here, going from 2 to 8x, I'm missing a factor of 4x. Crazy, I know. So, these examples are called the general power rule because what we're doing here is taking the derivative of my whole function, my big function. So let's say that I have f of x to the nth power. This is going to be n so whatever my exponent was, times my function. But then remember, we're going to do n minus 1, so we're just going to do the power rule. But then we're going to take the derivative of whatever is on the n-side function. So in this case, we're going to take the derivative of f prime of x, aka the n-side function. And that is the general power rule based off of our chain rule. In our chain rule, let's say that you are given a function inside of a function, because essentially that's what we saw here in these couple examples. We had a function within a function. So let's say that here, our power rule was x squared, and my x was x plus 1. Or here, where I had x to the third, my x was 2x plus 1. So here, my chain rule, if I have something inside f of g of x, I am going to take the derivative of this, so f prime of g of x, but then I'm going to take the derivative of the inside function. So you're going to take the derivative of the outside function first, and then take the derivative of the inside function. So outside, and then inside function. So think about it in terms of, let's say, a blow pop, where you want to get the gum. But in order to get the gum, you kind of need to break apart the candy pieces, the lollipop first, aka the outside, to get the inside, aka your gum. Or think about it in terms of a peanut M&M. In order to get the peanut, you need to crack open the shell. So your outside, the shell, to get the inside, aka your peanut. So here, if I have, let's say, e to the 3x squared plus 4x, I want to look at this in terms of, hey, what type of function do we see that we know we could take the derivative of? Here, we could see that we could take the derivative of e to the x. So here, e to the x is going to be my inside function, or outside function. So here, I'm going to say e to the 3x squared plus 4x. And then I'm going to take the derivative of the inside function, which is going to be 6x plus 4. Now, I'm going to give you a little warning. Once again, this is where your parentheses matter, because if you give me something like this right here, this is going to be interpreted as 6x times e to the 3x squared plus 4x, but that's not what we want. Remember, what we want is e to the 3x squared plus 4x times, parentheses, 6x plus 4. So make sure that you're using your parentheses whenever we are dealing with these types of problems. Same thing with quick example number 2. Let's say that we have sine of 3x squared plus 4x. You'll notice that my inside function is 3x squared plus 4x. My outside function is just going to be sine of x. So the derivative of sine is cosine. So I'm going to do 3x squared plus 4x, because that's still technically my inside function. And then I'm going to take the derivative of my inside function, which is just going to be, once again, 6x plus 4. And that, folks, is your chain rule. Lots of fun. Let's see. I'm going to do 11 because 11 seems a lot of fun right here. 11 is another concept of the chain rule, but you'll notice that we're going to have to use chain a couple of times. See how here we have an inside function of e to the x squared. My outside function is sine, so I am going to take the derivative of that. The derivative of sine is cosine, and then we have e to the x squared. Now I want to take the derivative of e to the x squared, but what you notice here is that we still have technically another function within a function, because we have e to the x, and then we have this x squared right here. So take the derivative of this, we're going to have to use chain again, where we have the derivative of a to the x, which is just a to the x, and then x squared, since this is technically x squared. And then we're going to take the derivative of the exponent. That's just going to be 2x. So this right here is my derivative of sine of a to the x squared. Lots of fun, I know. All right, in the next video, we will talk about implicit differentiation, which is also fun. This unit is so much fun.